In modern mass spectrometry, we rarely use electron impact mass spectrometry. Instead, we favor soft ionization methods in order to observe the molecular ion peak more clearly. So as shown here, electron impact will expel electron from the compound. In this case, we do see a molecular ion peak, but the spectrum is dominated by fragmentation. On the other hand, chemical ionization protonates the structure so that the cation is directly observed by mass spectrometry. With more complex compounds, even classical chemical ionization may result in fragmentation. And so even milder methods, including field desorption, have been developed which will favor molecular ion determination. At Emory, our core facility typically uses electrospray ionization for several applications. For small molecules, this is generally conducted as atmospheric pressure chemical ionization as an alternative to field desorption, but tends to favor formation of a molecular ion peak, and some informative fragments may be formed on occasion. If the structure has Lewis basic sites, such as oxygen atoms, coordination with silver cation tends to enhance molecular ion detection. A silver cation will coordinate with any one of the oxygens, and so we will see an M+23 peak as the principal peak. And this is typically used for high-resolution mass spectrometric methods. You can see that the electron impact spectrum is basically worthless. For the sample analysis by electrospray ionization mass spectrometry, the mass spectrometry operator will spike the sample with a tiny amount of sodium iodide. Electrospray ionization mass spectrometry is particularly valuable for analyzing biomolecules. The example from the textbook with a tetrapeptide is actually not that impressive, although it was provided to emphasize how the protein might potentially be sequenced by fragmentation. But what's more powerful is electrospray ionization mass spectrometry at high resolution on proteins, such as myoglobin. This page comes from another textbook authored by Phil Cruz, Craig Jaspers, and Marcel Rodriguez, with a peptide which has a large number of basic sites. Electrospray ionization will protonate the compound in multiple positions, giving a mixture of ions with a large number of positive charges. The electrospray ionization spectrum will give mass over charge, but it does not automatically tell us the charges. So erasing the charge data gives us the actual spectrum that we get from electrospray mass spectrometry. We can actually determine the charges for each peak and the overall molecular mass of the protein using these two formulas. These are based on the differences in masses for neighboring peaks that arises from this part of the formula. And notice that the difference decreases as we go from higher weight ions to lower weight ions. In fact, you can solve the charge for any peak and the overall mass of the macromolecule by analyzing any pair of neighboring peaks. In this specific case, we can determine the charge by analyzing two peaks. So we'll label this one M1 and this peak M2. We can then determine the charge, which is going to be M1 minus the isotopic mass of protium. And so that is the 6 significant figures, this value, divided by the difference between M over Z for M1 and M2, which is 108.66, which is this difference. The number N, which is the charge on M2, is equal to 13. Feel free to rewind a couple of minutes if you want to check this. However, we can reliably say that the other peaks are plus 12, in this case plus 14, plus 15, and so on. Now that we know the charge for a specific peak, we can determine the molecular mass. Following the formula, charge of 13 times molecular mass 2 minus the isotopic mass of protium. And this gives a molecular mass for the protein of 16,951.0 atomic mass units. We can give this value to 6 significant figures because each of the data points with high-resolution electrospray ionization has 6 significant figures. But each peak has a mass over charge of no more than 1,500.